I've come upon the opportunity to go to San Francisco for a few days with my sweet wife person. And as soon as she hears about any opportunity to go someplace, she's already bought the tickets. So we'll take off this afternoon, and I'll be back no later than next Friday, and my first activity on return will be to generate bonus quiz 2. Now then, a comment for whatever it's worth. Last night, if for nothing else but to satisfy my own curiosity, I redid our experiment to get at the solubility of calcium carbonate in ammonium chloride solution, 1 molar. I did this by remaking the ammonium chloride solution, and now got again an acceptable pH reading and good results. I don't know what's going on. Was the ammonium chloride solution, which I had used for our investigation during class last time, was also freshly prepared. It was only a day old. And when I first observed the pH of that ammonium chloride solution, the one that we had used, on the previous evening, right after I made it, I got 505. And yesterday when not yesterday, but Thursday when we tried this, I had started with 522. I don't know what's going on. Maybe the evil chemistry spirits are attacking my reagents when I'm not looking. If that's the case, I'll fight back, because I have reagents to attack the evil chemistry spirits. We'll see what happens. If I can get this debugged, we'll do it again. Because indeed it should work. There's no reason why it should not work. In any case, regarding the determination of the solubility of calcium carbonate in the ammonium chloride solution, we can rest upon the detailed analysis that we made, which involved material balance and charge balance considerations. The primary considerations of such we wrote on the board. So, to wrap up what we have so far considered, or bring it all together in Chapter 19, let's get back to this issue, saturated calcium hydroxide solution, and how does it react as a consequence of the various changes which we choose to apply. We looked last time at addition of calcium chloride solution and addition of sodium hydroxide solution and addition of water. And we left with this consideration. Again, this order of addition considerations is somewhat out of order relative to the list that you see in the notes. Just to remind you so you'll follow along. Add 1 molar ammonium chloride solution. I don't know why. I put in that set of lines. Clearly, the calcium hydroxide is going to dissolve readily. The main reaction that will occur will be the attack of calcium hydroxide by hydronium ion. Calcium ions AQ and water will be the products. You can write this reaction equation. There's nothing to it. The calcium ion molarity has got to increase, and the hydroxide ion molarity has got to decrease. So I believe we asked you these questions regarding this treatment. What impact does this treatment have on pH? What impact does this treatment have on calcium hydroxide solubility? What impact does this treatment have on the original equilibrium? Well, clearly the reaction of calcium hydroxide with hydronium ion is different from its simple dissociation in straight water. And if we add enough hydrochloric acid solution, we'll kill this equilibrium entirely, because we'll dissolve all the calcium hydroxide. So, the question as we are choosing to ask it, or the questions as we choose to ask them, are in regard to adding some hydrochloric acid solution, but not enough to dissolve all the calcium hydroxide, so that after this reaction takes place, that equilibrium condition will still exist. What will happen to the system pH? Well, ever so obviously, this treatment attacks hydroxide ion. It's got a lower system pH. But what impact does this equilibrium have on calcium hydroxide solubility? As a consequence of taking, we had this on the board, calcium hydroxide. Add enough HCl to reduce the amount of calcium hydroxide, say to this much. Doesn't matter how much, as long as there's some left. By this treatment, what have I done to the solubility of calcium hydroxide? Have I increased the solubility? Have I lowered the solubility? Or has the solubility of calcium hydroxide remained the same? How does this system inventory after we have treated it with the HCl solution? The answer is really on the board. Let's imagine I had 1 mole calcium hydroxide and added enough HCl to leave behind a half a mole of undissolved calcium hydroxide. How much hydronium ion will we have to add to in order to get this change to take place? How much HCl solution if it's 1 molar? How many moles of hydronium ion do we have to add to get this change to take place? How much? If I want to dissolve a half a mole of calcium hydroxide, I got to add a mole of hydronium ion, don't I? All right? So that would mean adding a liter of that stuff. So we will have built up the system volume. And we now ask again the question. In this system, as it now stands, after we did this, what happened to the solubility of calcium hydroxide? Has it remained the same, gone down, or gone up? What do you want to write in there? Lower or higher? How many vote for lower? How many recognize that this treatment has now produced a system in which the calcium ion molarity is damn high? You agree? If I dissolved a half a mole of calcium hydroxide, I got calcium ion in there that's now on the order of half molar. Right? What impact does that have on the solubility of calcium hydroxide? If I try to dissolve calcium hydroxide in straight water versus trying to dissolve calcium hydroxide in the system in which the calcium ion molarity is half molar, where's the calcium hydroxide a lot more soluble? Straight water. And how do I come to all these realizations? I always pay attention to PSI, right? If you pay attention to the nature of the system, you always have a chance to resolve these issues and understand what's going on. We proceed. Add calcium hydroxide. Well, I think that's going to make the amount of it go up. What's that going to do to the calcium ion molarity? No change. Hydroxide ion molarity? No change. The addition of sodium chloride is just salt effect. So the amount of calcium hydroxide will come down. Some additional will dissolve. And it will be found to be the calcium hydroxide, now somewhat more soluble than it is in straight water. The impact of salt effect on solubility is not extreme, but it's greater than what you find with straight water salt. So these molarities will go up. Now, how about sodium carbonate solution addition? I got this system. I'm going to supply to it carbonate ion. What's going to happen? Can I, in essence, kill that equilibrium by supplying carbonate ion? Products? What do we know about the solubility of calcium carbonate compared to that of calcium hydroxide? This is clearly a basic system. In a basic system, which material is much more stable, of much lower solubility? The carbonate or the hydroxide? Carbonate. You're doing this in lab. And we've already discussed it in detail in class when we talked about how to test for calcium ion by precipitation and wrote the KSP values for hydroxide, carbonate, and sulfate on the board and said if we have carbonate or hydroxide or sulfate each fixed at 10th molar, which of these things is easiest to form, and found out it was the carbonate by far. Well, on the recognition that calcium carbonate is less soluble, more stable than calcium hydroxide, that supports the conclusion that this reaction is a reaction with a large K value? Yes or no? Yeah. How am I going to find the K value? I look at this thing, I let it talk to me. We've done this. Now let's do it again. I see this equilibrium as nothing more than a composite of this salt of limited solubility in water being converted to this salt of limited solubility in water. So this K value is a composite of KSP for these two salts. Which KSP is on top? Which KSP is on the bottom? Hydroxide is on top. It's on the left. Remember how KSP is defined? Salt on left, component ions on right. Here, salt's on the right. So the component ions by default will be on the left. Well, in the notes we use 3.0 times 10 to the minus 5 for this, 6.2 times 10 to the minus 9 for this. At a glance I see this is a big number. So, if 1.0 moles calcium hydroxide. With 1.0 liters of 1 molar sodium carbonate. What do I expect to wind up with quantitatively? For this thing, There's K. What do I expect to wind up with if I do this in the lab? Do I expect to convert some of the calcium hydroxide to calcium carbonate? Absolutely. How much of it? How much? Want to make a bet? Well, I'll write this as 2x quantity squared. X is the amount of calcium hydroxide I convert. So down here I'll have 1.0 minus x. This K value you could see it at a glance is on the order of 500 times 10 cubed. Not 500, but 5, pardon me. It's really 4.8 times 10 cubed because this number is a little bit bigger than 6. If you deal with this problem from this algebraic standpoint, what are you going to find out? What will you find out about the value of x compared to 1.0? With k being 4.8 times 10 cubed. What will you find out about the value of x compared to 1.0? Is x a lot smaller than 1.0? Is x damn near 1.0? Then what am I going to expect to produce by this mix? More specifically, I've provided here with the information 2 sig figs. The 2 sig figs, how many moles of calcium carbonate do you think you can make? 1.0. It'll all convert to 2 sig figs. You'll have to go to 3 sig figs to find some unconverted calcium hydroxide. You do the arithmetic. You need the practice. All right? Now, one more consideration. Let's take this equilibrium and hammer it with 1 molar ammonium chloride solution. Now then, reaction equation. You know how to calculate these K's. Before you calculate K for this, you expect to get a large value for K relative to 1? Expect to get a value for K that's a lot bigger than 1 or on the order of 1 or smaller than 1. In other words, we're asking you, how effectively do you think ammonium ion attacks calcium hydroxide? We know ammonium ion does not effectively attack calcium carbonate, does it? Ammonium ion attacks calcium carbonate more effectively than water, but it does not attack calcium carbonate effectively. We analyze that system. K for that was 7.2 times 10 to the minus 8. What kind of K do you think you're going to get for this? Well, you know how to calculate the K. I'll leave that part up to you. If you have questions on it, you can ask us. But at a glance, you can see this reaction. K for this thing is going to be KSP calcium hydroxide in the numerator. And what else is going to be part of this K? K ammonium ion or Kb ammonia? Either one. If I use Kb ammonia, will Kb ammonia be numerator or denominator? Denominator. If I use Ka ammonium ion, Ka is going to be numerator, denominator? Numerator. Won't change the value. And will this Ka, if I use Ka ammonium ion, be first order? First power? What's this mean? Squared. Ready? So what do you think you're going to get? Wait, I think I misled you. We will, I think, by default be obligated to use Kb ammonia because this is going to be a composite of calcium ion and hydroxide ion. Right? So we're looking at ammonium ion denominator, ammonia numerator, and hydroxide ion numerator. So this will put Kb ammonia squared in the denominator. So you wind up with K being this. There's KSP calcium hydroxide. There's Kb ammonia quantity squared. Just give me a big number. So this reminds us. And I hope those of you in 46L will remember, you did this in lab. The first salt of limited solubility, which you prepared and observed properties of, was calcium hydroxide in assignment 3. And you were asked to do an investigation to find out about the readiness of dissolving calcium hydroxide by ammonium ion treatment. You did this. How many remember what happened? The calcium hydroxide dissolved readily? What's that case suggest? Dissolve readily? You're damn right. Calcium carbonate, ammonium ion, 7.2 times 10 to minus 8. Look what happens when we change the semi-soluble salt to calcium hydroxide. A huge difference. This is readily dissolved by ammonium ion. What's the difference? A lot of difference. Well, calcium carbonate, we know to start with, is a salt of greater stability. Lower solubility than calcium hydroxide. That shouldn't be too surprising, because the component ions of calcium carbonate are +2 and -2 respectively. Calcium hydroxide +2 and -1. So you're not going to have nearly as effective coulombic attractions. And you'll also have a lattice problem, but I don't know if you talked about ionic lattices in 2045, so we won't talk about the lattice problem. We also know that if I hit calcium carbonate with ammonium ion, I convert carbonate principally to bicarb ion. So I'm not really removing a precipitating agent from the system, am I? I still got a carbonate source in there. But when I protonate hydroxide ion and turn it into water, forget it. I killed the hydroxide. And hydroxide ion, ammonium ion. Bronsted-Lowry acid-base reaction extent versus hydroxide ion, carbonate ion. Pardon me, versus carbonate ion, ammonium ion. Carbonate ion, ammonium ion versus hydroxide ion, ammonium ion. Which one is a much larger extent acid-base reaction? Ammonium ion, hydroxide ion. Hydroxide ion is a lot stronger base than carbonate. You got a K value for ammonium ion plus hydroxide ion? Ammonium ion plus carbonate ion. K value is about 10. You know how to calculate it. Ammonium ion plus hydroxide ion. How do I get the K value? Ammonium ion plus hydroxide ion. Products, ammonia and water. How do we get the K value for that reaction? Isn't that 1 over Kb ammonia? Well, what's 1 divided by 1.8 times 10 to the minus 5? Is that a big number? You're damn right. So we now sized up the thermodynamic factors which tell us why the calcium hydroxide is a lot more soluble, a lot more amenable to attack by ammonium ion compared to attacking calcium carbonate by ammonium ion. All right? So, we'll ask another question. Now I'm going to shake 1.0 moles of calcium hydroxide with 1.0 liters of ammonium chloride solution. Previous consideration was the 1 mole of calcium hydroxide with the 1 liter of 1 molar sodium carbonate solution. And we recognize that practically all the calcium hydroxide becomes calcium carbonate. Now we're talking about, again, a mole of calcium hydroxide, but this time we're going to attack it with 1.0 liters of 1 molar ammonium chloride solution. The K tells us calcium hydroxide is readily attacked, effectively attacked by ammonium ion. How much calcium hydroxide will I dissolve? By this mix. How much calcium hydroxide am I going to dissolve? How much? How much? Yup! How much?
1.0 moles.
0.50 moles. Damn it! Look at the stoichiometry of that. I need 2 moles of ammonium ion if I want to beat up a mole of calcium hydroxide, don't I? Ha ha ha. That was a nasty trick, wasn't it? Not really. All right? What about this? Going back to the original system. Will this have an impact on the original system? Will this have a significant impact on the original system? We just found out ammonium ion murders calcium hydroxide. Has this got ammonium ion in it? In fact, on a per mole basis, it got 2 moles of ammonium ion. What else has this got in it? Sulfate ion. If I hit calcium hydroxide, with this, what am I going to do? What's going to happen? How much? 1 mole, you betcha. And what else? If I make this mixture, would you like to hang your nose right over the beaker in which you make the mixture and take a deep breath? Because the ammonia coming out of there is going to flatten you. But the fate of calcium ion from calcium hydroxide originally will now be to incorporate calcium ion into this stuff, gypsum. What about K value? Let's put down K value CT compared to 9.3 times 10 to the fourth. That's the K value that I get when I hammer calcium hydroxide with ammonium ion. Now I'm hammering calcium hydroxide with ammonium ion as well as sulfate ion. What kind of K value will I get relative to this? Much larger? 10 times larger. How about maybe even 20 times larger? How about maybe 100 times larger? How about 1,000 times larger? How about more than that? How about that? You can calculate the K. Not only do I have ammonium ion to murder calcium hydroxide, I have sulfate ion to gobble up the calcium ion. In my ammonium ion attack, I don't have anything to gobble up calcium ion. Now I got a sulfate now I got sulfate in there to gobble up calcium ion. Does sulfate ion gobble up calcium ion better than hydroxide ion? Is calcium sulfate less soluble, more stable in water than calcium hydroxide? You're damn right. If I put these thermodynamic puzzle parts together, then I know what's going on. Okay? You do the K-calc. You know how to do it. Now, three choices. Imagine you are in the laboratory. It's better than close to. I got 1.0 times 10 to the 10 for that K value. You're in the lab. You got calcium hydroxide. I come in and I command you to convert all the calcium hydroxide to calcium sulfate. And everybody says, that SOB Horvath here, he just told us to do this, we better do it. Okay, so now you understand the command. How do you do it? I give you three choices. Ammonium sulfate solution, 1 molar. Sodium hydrogen sulfate solution, 1 molar. Or sulfuric acid, 1 molar. Your job is to convert calcium hydroxide to calcium sulfate. What is your selection? From a thermodynamic analysis standpoint, you'd write each reaction equation and calculate the K. Which choice would you make? Which is going to have the highest K? What do you think? Sulfuric acid solution. Any other votes for sulfuric acid solution? Would you accept the statement that sulfuric acid solution certainly attacks hydroxide ion more strongly than any of the other systems, because the sulfuric acid solution is the one which is richest in hydronium ion by far? And hydronium ion is a much stronger acid than hydrogen sulfate ion, and a much, much stronger acid than ammonium ion, right? And like hydrogen sulfate solution, sulfuric acid solution is also a good source of sulfate ion, because they're each rich in hydrogen sulfate ion. That's it. You do the K analysis to find out. If you have any trouble, you can ask us. Now, with that, I want to jump to the very last part of chapter 19, which reads, this is section 19-4. The remaining attack consideration regarding rendering a salt of limited solubility in water to become soluble. Specifically, I want to look at this reaction, because this reaction involves the formation of this complex ion. Kf, the formation constant for the equilibrium reaction involving the formation of its complex ion from its component species, has this value. Does that sound like this is a pretty stable ion? You betcha. There's the equilibrium reaction. It's in the notes. Now then, some of this stuff we're jumping past, but we will return to it on our first gathering following the great grand spring break week, during which I expect you to spend all your time studying chemistry. Is that correct? Don't answer. I don't want to go to San Francisco in a snit. Let's build up the system of this, not system, let's build up volume for the system we're going to prepare with some deionized water. The label's kind of scorched, but... All right. Now in this deionized water, I'm going to add a good slug of silver nitrate solution, 200 molar, the same source of silver ion which you folks use in the laboratory. Now then, after adding the silver ion along with nitrate ions, I'm going to add a good slug of 1 molar sodium chloride solution. What do you expect to observe? What do you expect to observe? Anything? You expect to observe the formation of a solid? Specifically, what solid? A milky appearing system. But if we allow it to stand, pretty soon the white stuff which is kind of off-white silver chloride, will settle to the bottom because it's more dense than the water part of the mix. But at the moment, most of the silver chloride is distributed throughout the system because silver chloride is of such low solubility that this reaction forms silver chloride, boom, just like that. So you got a bunch of little tiny particles. That's why they remain suspended. But never mind that. We put together silver ion with chloride ion and made silver chloride. Kind of described oftentimes as curdy white. You know what the word curdy means? You ever seen spoiled milk? Curdled? Not particularly crystalline. We'll find out with later conversation that silver chloride is mainly covalent in character rather than ionic. Now, I'm going to treat with some 6 molar ammonia, my ammonia source. What do you expect to see? Magic! The silver chloride went away. What did the silver chloride become? Became chloride ion AQ and this stuff. You saw the experiment. We just did it. You will also do this on your own in 46L assignment 6. So we ask a question. Which forms stronger bonds to Ag plus? Cl minus or ammonia? What do you think? All right, we got votes for ammonia. You will find out your vote is dead wrong, but that's okay. Now then, one more question. The system we just prepared is now going to be treated with nitric acid solution, 6 molar. To system from Ag plus Cl minus plus H3N. Put silver ion in first, added chloride ion to generate silver chloride, added ammonia, which you saw caused the silver chloride to dissolve and disappear readily, and now we're going to add 6 molar nitric acid solution. What will happen? Will the silver chloride come back? Will the addition of hydronium ion kick the living hell out of ammonia and beat the hell out of that complex because it's got ammonia molecules in its composition? So we expect the silver chloride precipitate to come back. Will we observe anything else? Now I'm going to do this. We've already really recognized that when I hit the liquid part of this system, with the nitric acid solution, the silver ammonia complex will be destroyed, the ammonia molecules will be killed, and chloride ion will now have the opportunity to rebond with silver ion. That'll reform silver chloride. There's a little bit of opacity in there, so we'll put some more ammonia in there. There. Now we're going to put the nitric acid solution in there. I want you to keep your attention focused, not here where the silver chloride will be reproduced, but up here. Got that? See the smoke? What is the smoke? I expect you all to be able to answer this when we get back together immediately following spring break.